In the vast expanse of space where starlight pierces the darkness, humanity stands on the threshold of its greatest discovery. For centuries, we have gazed at the night sky, dreaming of worlds beyond our own. First, we conquered the oceans, then the continents, and in the 20th century, we dared to venture into space. But amidst all these triumphs, Earth remains our only home, the cradle of life as we know it. However, shadows are gathering over our cozy world. The climate is changing like a capricious beast. Global warming threatens to melt the eternal ice, and biodiversity is disappearing like morning mist. Pandemics, like evil spirits, prowl the planet. The nuclear threat looms over us, and overpopulation weighs on resources like an unbearable burden. Despite our technological progress and ability to adapt, there are limits. And so we are faced with the question, what if Earth becomes uninhabitable? That's why the search for other planets capable of supporting life is becoming not just science fiction, but a vital necessity. Imagine, somewhere out there in distant galaxies, there may be a second home for humanity, a place where we can continue our journey if our home planet can no longer accept us. But how far have we come in this search? What secrets does the universe hold? And what awaits us as we embark on the quest for a new home? The answers to these questions could change everything, and you'll find out by watching this video to the end. It also seems highly significant that Earth is not the only haven for life in the vastness of the universe. With the steady progress of science, astronomers are increasingly discovering exoplanets, celestial bodies located outside our own solar system that appear to be capable of supporting life. Studying these distant worlds could be a crucial step toward understanding our future, as some of them may have Earth-like conditions. So, what are exoplanets? These are planets orbiting stars outside our solar system. Until the 90s, their existence remained only a hypothesis, but with the advent of new astronomical instruments, such as powerful telescopes and radio telescopes, scientists have obtained more and more confirmation of their reality. In '95, astronomers Michel Mayor and Didier Queloz made a breakthrough by discovering the first exoplanet orbiting a star similar to our Sun, 51 Pegasi. This discovery was a turning point in astronomy and marked the beginning of a new era in space exploration. Since then, astronomers have discovered thousands of exoplanets, and their number continues to grow every year, opening up exciting prospects for humanity. Currently, the scientific community confidently declares the discovery of many celestial bodies with the potential to support life. These exoplanets may have Earth-like characteristics, such as being located in the habitable zone around their stars, where water can exist in liquid form, and having a suitable atmospheric composition. Interplanetary research opens new horizons for the future of humanity. The discovery of exoplanets and the study of their potential habitability is of paramount importance for the further development of civilization. But why should humanity look for a new home in space? The answer lies in several key arguments. First, it is a matter of survival. Earth is not an eternal refuge. In a few billion years, the Sun, having exhausted its reserves of hydrogen, will begin to turn into a red giant, which will lead to irreversible climate changes and make conditions on Earth uninhabitable. In addition, there are other threats, such as collisions with asteroids, global conflicts with the use of nuclear weapons, large-scale climatic cataclysms, and other unpredictable events that may occur much sooner. Secondly, the study of exoplanets opens up long-term prospects for the development of science and technology. In addition to expanding knowledge about the universe, these studies stimulate the development of innovative technologies that can solve pressing problems of humanity, such as the energy crisis and ensuring food security. Transforming other planets into potential cradles of life, known as terraforming, opens up not only the prospect of expanding living space for humanity, but also valuable knowledge that can transform the environmental situation on Earth. Research in this area stimulates the development of innovative approaches to protecting the atmosphere, restoring water resources, and preserving biodiversity. The vastness of space holds not only the possibility of creating new settlements, but also an inexhaustible source of resources. Exoplanets located at a considerable distance from Earth may contain unique minerals and elements that are scarce or difficult to access on our planet. Rare metals crucial for the development of advanced technologies could become available through the exploration of exoplanets, opening new horizons for the global economy and innovation. The search for extraterrestrial life holds immense philosophical significance, touching on fundamental questions about humanity's place in the universe and the nature of existence itself. The discovery of extraterrestrial life forms, even the most primitive ones, could radically alter our understanding of the cosmos. Studying these life forms, which may differ significantly from anything known on Earth, will unlock new perspectives in biology, ecology, and philosophy, expanding the boundaries of our understanding of life as a phenomenon. The search for an extraterrestrial second home for humanity is not merely a scientific endeavor, but a pressing necessity, driven by the desire for survival, further progress, and an understanding of our role in the vast universe. We stand at the crossroads of epoch-making discoveries capable of fundamentally transforming the fate of human civilization. Chapter 1 focuses on defining the concept of a habitable planet and the key conditions necessary for supporting life. When discussing the search for potentially habitable worlds, it is important to have a clear understanding of the characteristics that make a planet hospitable to living organisms. Primarily, this involves parameters that ensure the existence of water in a liquid state, a stable climate, and the presence of necessary chemical elements. The presence of water is of paramount importance. Life as we know it is inextricably linked to water, a unique liquid that supports the chemical reactions necessary for the existence of living beings. Water acts as a solvent and a transport medium for substances that play a key role in metabolism. For a planet to be considered potentially habitable, one of the main criteria is the presence of water in liquid form. The habitable zone, or Goldilocks zone, is the region around a star where temperature conditions on the planet's surface allow water to remain in a liquid state. The size of this zone depends on the temperature and luminosity of the star. If a planet is located too close to the star, its surface will become scorched and water will evaporate. Conversely, if a planet is too far from the star, the water will freeze, turning into ice. The habitability of planets is determined by the type of star, and only those within the so-called life zone can potentially possess conditions resembling those on Earth. However, the presence of liquid water is just one of many factors necessary for the emergence and sustenance of life. Atmospheric characteristics are also crucial, providing reliable protection from harmful cosmic radiation and ensuring climate stability. Ideally, the atmosphere should be enriched with oxygen, necessary for respiration, and carbon dioxide, which plays a key role in creating the greenhouse effect that maintains the temperature on the planet's surface within acceptable limits. Equally important is the presence of certain chemical elements, such as carbon, nitrogen, oxygen, and hydrogen, which are fundamental components of all living things. These elements must be present in sufficient concentrations to support the chemical reactions that underpin biological processes. The combination of a suitable atmosphere and an optimal chemical composition creates a favorable environment for the development of organisms in diverse forms and ensures the long-term stability of ecosystems, which in turn is necessary for the existence of life as we know it. In the process of searching for planets potentially inhabited by living organisms, it should be taken into account that all our ideas about life are based on terrestrial experience. Our understanding of life as a phenomenon is currently limited to the biosphere of Earth. It is quite possible that there are forms of life in the universe based on completely different elements or chemical processes, different from those known to us. However, until science manages to discover such exotic forms of existence of matter, we will proceed from the assumption that life is a complex process based on carbon compounds and water. Life on Earth is striking in its diversity, from single-celled microorganisms to multicellular plants and animals. For the existence of all these life forms, certain conditions are necessary, such as a stable ambient temperature, the availability of food and water sources, and effective protection from the harmful effects of external factors such as radiation or extreme temperatures. Therefore, for planets claiming the title of potentially habitable, it is crucial that the conditions on their surface remain stable enough to support sustainable ecosystems. The composition of the atmosphere and the level of radiation emitted by the central star are equally important. The intensity of radiation can vary significantly depending on the type of star and the age of the planet itself, which directly impacts the possibility of life as we know it. In the fascinating field of exoplanet research, special attention is paid to celestial bodies that, while located outside the generally accepted habitable zone, may still harbor life. Subterranean oceans hidden beneath icy crusts or surfaces unsuitable for known life forms present an intriguing possibility for the existence of living organisms. For a planet to support life, it must meet several crucial criteria. First and foremost, the size of the planet is critical. A sufficiently large celestial body has the gravity to hold an atmosphere. A planet that is too small risks losing its atmosphere due to insufficient gravity, rendering its surface lifeless. Temperature is also crucial. An optimal temperature is necessary to maintain liquid water, which is essential for supporting life. The temperature on the surface of a planet is determined by its distance from its star, the composition of its atmosphere, and other factors. A habitable exoplanet should have an average temperature at which water can exist in liquid form, which is one of the primary criteria when selecting candidates. The atmosphere of a celestial body plays a defining role in the possibility of life on it. It acts as a reliable shield, protecting the surface from the destructive effects of cosmic radiation and constant meteorite attacks. In addition, the atmosphere functions as a thermostat, maintaining a favorable temperature regime through the greenhouse effect. Otherwise, if the planet's atmosphere is too thin or filled with poisonous gases, the emergence and maintenance of life become impossible. The composition of the atmosphere is also of paramount importance. On Earth, nitrogen, approximately 8%, and oxygen, approximately 21%, predominate, and this harmonious combination creates conditions for the prosperity of all living things. Other planets have different atmospheric combinations, but for the existence of life in the form we know it, a balanced composition of chemical elements, including carbon dioxide, water vapor, and oxygen, is crucial. The planet's magnetic field serves as an additional barrier, reflecting streams of solar radiation and protecting the atmosphere from destruction. In the absence of a magnetic field, as observed on Mars, the solar wind gradually dissipates the atmosphere, making the planet uninhabitable. The stability of the star around which the planet orbits is also important. A star that is too active or variable can be a source of excessive radiation or powerful flares, which poses a serious threat to any form of life. Planets in the habitable zone, between fiction and reality. It is a common misconception that planets located in the so-called life zone automatically become cradles for living organisms. However, the reality is far more complex. The habitable zone is merely a starting point in the painstaking process of searching for extraterrestrial life. A good example is Venus and Mars, our closest cosmic neighbors, located within the habitable zone of the solar system. Alas, neither of these worlds can boast favorable conditions for life. Mars is bound by eternal cold and almost devoid of a dense atmosphere, while Venus is tormented by unbearable heat, and its atmosphere, consisting mainly of carbon dioxide, creates a greenhouse hell effect. Thus, being in the habitable zone is a necessary but not sufficient condition for the existence of life. Another common belief is that to discover life beyond Earth, we should focus exclusively on planets that are as similar to our own as possible. However, this approach may significantly limit the prospects of the search. Some scientists put forward bold hypotheses that life is capable of adapting to completely different conditions than those on Earth. Take, for example, Europa, a satellite of Jupiter. Beneath its icy crust, there may be entire oceans where living organisms may exist, safely protected from harsh external conditions. In conclusion, it should be emphasized that the search for habitable planets is a complex task that requires consideration of many factors. From the chemical composition of the atmosphere to the presence of a magnetic field, every detail matters when it comes to determining the potential habitability of a celestial body. Chapter 2. Exoplanet Research. How researchers discover new worlds. The discovery of exoplanets is one of the most exciting and ambitious tasks facing modern astronomy. Exoplanets do not emit their own light, making their detection extremely difficult in the vastness of space, where stars shine much brighter and distances are measured in light years. Nevertheless, through the use of advanced technologies and innovative methods, scientists have been able to discover thousands of exoplanets, among which there may be some that are suitable for life. One of the key ways to detect exoplanets is the transit method. It is based on observing an exoplanet passing in front of its star, which causes a slight decrease in its luminosity. This allows astronomers to estimate the size of the planet, the parameters of its orbit, and other characteristics. For this, ground-based and space telescopes are used, which have high sensitivity and are able to register even the smallest fluctuations in the brightness of stars. Another important method is the radial velocity method, also known as the Doppler method. It consists of measuring the oscillations of a star caused by the gravitational influence of a planet rotating around it. These oscillations lead to a change in the frequency of light that we observe from the star. The star begins to make small movements under the influence of the planet's gravity, and this becomes noticeable, even if the planet itself remains invisible. This method allows us to determine the mass of the planet, the parameters of its orbit, and in some cases to detect exoplanets located at a considerable distance from their star. Along with this, researchers of space have the method of direct observation in their arsenal, although it is associated with considerable difficulties. Its essence lies in using the most powerful telescopes to see an exoplanet. This requires not only telescopes with incredibly high resolution, but also the ability to filter out the blinding light of the star in order to distinguish the faint flicker emanating from a distant planet. So far, this method has not been widely used, since its implementation requires tools that surpass everything that has been created before in terms of capabilities. For example, the James Webb Space Telescope. However, progress does not stand still. Every year, new methods appear, and telescopes are improved, which makes the search for exoplanets more and more effective and accurate. Thanks to these achievements, scientists are able to discover exoplanets in the most remote corners of the universe, which undoubtedly opens up exciting prospects for future research. Space telescopes play a special role in the study of exoplanets, becoming a real breakthrough in astronomy. One of the most famous among them is the Kepler telescope. In 2009, the Kepler telescope mission started, marking a new era in the study of exoplanets. During its operation, Kepler discovered more than 2,500 exoplanets using the transit method, which had a tremendous impact on the development of astronomy. Despite the completion of the mission in 2018, Kepler's discoveries continue to serve as a valuable source of information for the study of exoplanets. In 2018, the TESS telescope took over, focusing on the search for exoplanets in the nearest star systems. Over several years of operation, TESS has discovered more than 60 new exoplanets. The uniqueness of TESS lies in its ability to explore planets in close proximity to us, which significantly increases the likelihood of discovering planets that are promising for further research and possible colonization. The launch of the James Webb Telescope in 2021 became a truly revolutionary event in astronomy. This powerful instrument, equipped with advanced technologies, allows astronomers to explore exoplanets in the infrared spectrum and determine the composition of their atmospheres. Thanks to its high sensitivity, James Webb is able to detect the smallest details, such as chemical elements in the atmospheres of exoplanets, which opens up new horizons in the search for life beyond Earth. Along with this, radio telescopes play a key role in the study of distant worlds, allowing us to study exoplanets that are inaccessible for observation in the optical range. Advanced instruments, such as ALMA and VLA, open up the opportunity for scientists to observe cosmic objects in the radio wave spectrum, providing valuable information about the processes occurring on exoplanets and their interaction with their stars. Over time, innovative methods appear that can radically improve the possibilities of searching for exoplanets. Special attention is paid to the development of planetary spectrographs designed to analyze the light passing through the atmosphere of exoplanets and determine its composition. These highly sensitive devices are capable of detecting the presence of chemical elements, such as oxygen, carbon dioxide, and methane, which can serve as indicators of the existence of life. At the same time, technologies are actively developing aimed at increasing the efficiency of exoplanet detection. Concepts are being considered for creating telescopes capable of collecting light from immense distances, which would allow the detection of exoplanets even in the most remote star systems. Such technological breakthroughs will help astronomers more effectively search for planets in habitable zones and significantly accelerate the process of their discovery. Exciting prospects are opening up in the field of applying laser technologies for detecting exoplanets. The latest research inspires hope that lasers can significantly increase the resolution of telescopes, allowing astronomers to study distant worlds with unprecedented detail. It is expected that in the foreseeable future, these advanced technologies will become a reality, opening a new era in the exploration of exoplanets and expanding the boundaries of our understanding of the universe. In addition to laser technologies, scientists are actively developing innovative methods for monitoring starlight. These methods are aimed at identifying even the slightest fluctuations in the brightness of stars, which may indicate the presence of exoplanets in their orbits. New algorithms and artificial intelligence systems play a key role in this process, allowing for rapid analysis of vast amounts of data coming from telescopes and accurately determining the location of exoplanets, as well as assessing their potential habitability. Despite significant progress in the search for exoplanets, scientists face a number of serious challenges. One of the most difficult tasks is determining which of the discovered exoplanets are truly suitable for supporting life. The vast distances separating us from these distant worlds make it impossible to directly study their atmospheres and surfaces. As a result, scientists have to rely on indirect data, which does not always provide a complete and accurate picture of the conditions on these exoplanets. However, the desire to find planets beyond our solar system is limited by the boundaries of modern technology. To detect exoplanets located at unimaginable distances, telescopes of colossal power and innovative observation methods are required. This process requires significant financial investments and technological advancement, which turns the search for exoplanets into a long-term prospect. Despite this, astronomy, technologies, and methods for searching for exoplanets are developing every year. In the coming decades, scientists hope to discover many exoplanets, including those that resemble Earth and have conditions potentially suitable for life. This opens up exciting prospects for humanity. The search for exoplanets has become one of the most significant tasks in astronomy, for which specialized space missions have been developed. These missions are designed to expand our understanding of conditions on other planets and assess their potential for the existence of life. In the chronicle of space exploration and the search for life beyond Earth, a special place is occupied by the Kepler mission, launched under the auspices of NASA in 2009. Its primary task was to discover exoplanets, celestial bodies orbiting distant stars, using the transit method. This method is based on recording the slightest changes in the light of a star when a planet passes in front of it, creating the effect of a miniature eclipse. Kepler, equipped with highly sensitive equipment, was able to detect more than 2,500 exoplanets within 3,000 light-years of Earth. It is important to note that a significant portion of these planets are located in the so-called habitable zone, where conditions theoretically allow water to exist in liquid form, and their characteristics are close to Earth's. This mission radically expanded the horizons of knowledge about potential conditions for the existence of life in the universe. After the completion of Kepler's work in 2018, the baton was picked up by a new space planet hunter, the TESS, Transiting Exoplanet Survey Satellite. The TESS mission, also launched in 2018, focuses on searching for exoplanets in the star systems closest to us. This device conducts more detailed studies of the discovered planets, seeking to identify those that may be potentially habitable. In addition, TESS collects data allowing scientists to understand how different types of stars affect the characteristics of the planets orbiting them. Over several years of operation, TESS has discovered a number of exoplanets that resemble Earth in size and characteristics, opening up new prospects in the search for habitable worlds. In the exciting race to understand alien worlds, a special place is occupied by the James Webb mission, which is one of the most promising projects in the field of exoplanet research. This new generation space telescope, which set off on its journey in 2021, opens a new era in astronomical research, providing scientists with unprecedented opportunities to study planets beyond our solar system. Unlike its predecessors, such as Kepler and TESS, James Webb possesses significantly greater sensitivity and can explore exoplanets in the infrared range, enabling the determination of their atmospheric composition. This opens exciting prospects for identifying key elements like water, oxygen, carbon dioxide, and methane, which may serve as indicators of potential life on these distant planets. The James Webb mission promises to be the primary tool for exoplanet research in the coming decades. Thanks to its unique capabilities, scientists will not only be able to discover new exoplanets, but also conduct detailed analyses of their atmospheres, study their chemical composition and temperature characteristics, and search for biosignatures, signs of possible life. The mission is also expected to detect exoplanets that previously remained unnoticed by other telescopes, thereby expanding the horizons of the search for potential candidates for the role of humanity's second home. Alongside powerful space telescopes, planetary spectrographs are being tirelessly improved to unlock the secrets of the chemical composition of distant exoplanets. By analyzing the spectrum of light passing through the atmospheres of celestial bodies, these instruments will enable scientists to discover elements and molecules that can serve as definitive indicators of the existence of life or favorable conditions for its emergence. In the foreseeable future, we can expect impressive technological breakthroughs that will significantly enhance the efficiency of exoplanet searching and detailed study of their characteristics. One such breakthrough direction will be the creation of ultra-powerful telescopes equipped with unprecedentedly high resolution. These giants will be able to peer into the most remote corners of space and explore exoplanets located at colossal distances. Innovative methods, such as gravitational lensing, will allow astronomers to observe planets located at such distances where traditional methods prove powerless. The introduction of artificial intelligence and machine learning will become another powerful tool in the hands of scientists, allowing them to process vast amounts of data from telescopes and other research instruments with unprecedented speed. This will lead to a significant acceleration of the analysis and search for exoplanets, as well as improve the accuracy of predictions. Artificial intelligence, like a tireless detective, will automatically analyze data on emitted light and identify potential signs of life, such as characteristic chemical elements present in the atmospheres of celestial bodies. At the same time, the horizons of astronomy are expanding thanks to the rapid progress in laser technology. Lasers open new opportunities for increasing the resolution of telescopes, allowing scientists to see clearer images of distant worlds. In addition, they provide high accuracy in measuring distances to exoplanets and tracking their trajectories. Thanks to these innovations, astronomers are able to quickly collect data that previously took years of painstaking observation. In the future, humanity may witness the birth of a new generation of space observatories, combining satellites and telescopes equipped with advanced instruments for directly studying exoplanets. These technologies will allow astronomers to study exoplanets in a wide range of the electromagnetic spectrum, from visible light to infrared radiation. Such a comprehensive analysis will make it possible to form a more complete understanding of the atmospheres, climate, and potential habitability of these distant worlds. The search for life beyond Earth is not only a priority for missions such as Kepler and TESS, but also a long-term goal that unites the efforts of scientists around the world. Using the most modern technologies, researchers seek to discover possible biosignatures, unique chemical or physical characteristics indicating the presence of life. For example, the presence of methane and oxygen in the atmosphere of an exoplanet may serve as convincing evidence of biological activity, since these gases in significant quantities are usually products of the vital activity of living organisms. In the exciting race to discover extraterrestrial life, Proxima Centauri b occupies a special place as one of the most likely candidates attracting the attention of scientists. Located within the habitable zone of its star, this exoplanet has become the object of close study in the hope of finding signs of life. Experts do not rule out the possibility of liquid water on its surface, which creates favorable conditions for the development of living organisms. With the development of technologies for the search for extraterrestrial life, scientists will be able to conduct detailed observations of exoplanets. In the coming decades, it is expected that it will become possible to analyze the atmospheres of these distant worlds at the molecular level, providing valuable information about potential signs of life. Despite significant progress, the search for exoplanets and the discovery of life on them are fraught with serious difficulties. One of the main problems is the colossal distance between Earth and exoplanets. Even the most powerful telescopes do not allow us to explore these worlds with sufficient accuracy to detect signs of life. Furthermore, the remoteness of many exoplanets makes it impossible to send research missions, which limits the amount of available data obtained through telescopes. It is important to emphasize that many celestial bodies of interest, from the point of view of potential habitability, may differ significantly from familiar terrestrial standards. For example, exoplanets located within the so-called habitable zone around their stars may lack an atmosphere suitable for the existence of terrestrial life forms. In such circumstances, they may be valuable for scientific research, but they will be unsuitable for future colonization efforts. Nevertheless, the colossal efforts undertaken by the scientific community in the field of exoplanet search and the study of conditions conducive to life open up exciting prospects for humanity. Forthcoming discoveries in this area will be crucial to understanding humanity's place in cosmic space. To date, astronomers have discovered thousands of exoplanets, including many candidates potentially capable of supporting life. These celestial bodies are located in the habitable zone of their stars, where temperature conditions allow water to exist in liquid form, which is one of the key signs of life known to us. It should be noted that in the process of searching for such planets, scientists face many factors that require careful analysis to confirm the possibility of life on an exoplanet. Some of the exoplanets discovered in the habitable zone have already attracted the close attention of the scientific community. A prime example of a celestial body attracting the attention of scientists is Kepler 442b, the discovery of which was made possible by the Kepler Space Telescope. This exoplanet, located a considerable 400 light-years away from us, is notable for its size and characteristics, which are in many ways reminiscent of Earth. It is assumed that conditions on Kepler 442b may be potentially favorable for the existence of life, provided there is liquid water on its surface and a sufficiently dense atmosphere capable of supporting life. Another celestial body of great interest to researchers is Proxima Centauri b. This exoplanet is located in the so-called habitable zone around Proxima Centauri, the closest star to Earth after the Sun. The distance to Proxima Centauri b is only 4.2 light-years, making it one of the closest candidates for the search for extraterrestrial life. The planet has a mass comparable to that of Earth and is located in a region where conditions for the existence of water in liquid form are theoretically possible. However, it should be noted that Proxima Centauri emits strong ultraviolet radiation, which may create obstacles to the development of life. Nevertheless, the question of the suitability of Proxima Centauri b for life remains the subject of active scientific research. Attention should also be paid to LHS 1140b, an exoplanet discovered thanks to the TESS Space Telescope. Located 40 light-years away from us, it has dimensions comparable to Earth's, making it an attractive object for studying potential habitability. Scientific research hints at the possibility of the presence of water in a liquid state in its atmosphere, which significantly increases the chances of the existence of favorable conditions for life. However, it is worth recognizing that determining the characteristics of exoplanets and assessing their suitability for life is not an easy task. Finding a planet in the so-called habitable zone is not yet a guarantee of its habitability. It is necessary to take into account a number of factors, including the composition of the atmosphere, the level of radiation, the presence of a magnetic field, as well as the presence of chemical elements necessary for the origin and maintenance of life. Kepler 452b is another celestial object that has received the unofficial nickname Earth 2.0 due to its striking resemblance to our home planet. This world, located 1,400 light-years away from us in the constellation Cygnus, is only % larger than Earth in size. Kepler 442b was one of the first exoplanets discovered in the habitable zone of its star. Based on its characteristics, scientists suggest that conditions on its surface may be similar to those on Earth, in particular the presence of liquid water. Despite its location in the potentially habitable zone around the red dwarf Proxima Centauri b faces significant obstacles to the development of life. The intense ultraviolet radiation emitted by its star creates harsh conditions. Nevertheless, the planet's proximity to the star theoretically allows for the presence of liquid water on the surface, which fuels scientific interest. LHS 1140b, an exoplanet comparable in size to Earth and also located in the habitable zone of its star, is a promising object for research. It is believed that the presence of a dense atmosphere may play a key role in sustaining life. Its relative proximity to Earth, only 40 light-years away, makes it particularly attractive for further observation and study. The TRAPPIST-1 system, located 40 light-years away from us, was a real discovery in the context of the search for exoplanets capable of supporting life. Scientists hypothesize that some of the planets in this system may have conditions conducive to the existence of liquid water, making them priority candidates for the discovery of extraterrestrial life. Celestial bodies located within the life zone around their stars attract close attention from scientists because it is in these areas that conditions are created for the existence of water in its liquid state, which is a key factor for the origin and maintenance of life. However, not all planets in this favorable zone automatically become cradles for living organisms. Each star has its own unique habitable zone, the size of which is determined by its mass and temperature. Stars with small mass and low temperature, such as red dwarfs, have a significantly smaller life zone compared to stars like our Sun. Therefore, exoplanets orbiting red dwarfs within their habitable zone must be much closer to their stars to ensure a surface temperature suitable for liquid water. However, this proximity also brings additional difficulties. For example, the powerful ultraviolet radiation emitted by red dwarfs can pose a serious threat to the planet's atmosphere, destroying its protective layer. In addition, even being in the habitable zone does not guarantee that a planet is suitable for life. There are a number of other factors that can affect the potential habitability of a celestial body. For example, the presence of a strong magnetic field that protects the atmosphere from the harmful effects of cosmic radiation is a prerequisite for the existence of life. Without reliable magnetic protection, a planet risks losing its atmosphere, which will make conditions for life impossible. The temperature regime on the surface of a celestial body is a determining factor in the context of potential habitability. It is important that the temperature indicators remain in a stable range, ensuring the possibility of the existence of water in the liquid phase. At the same time, it is critical to avoid excessive temperature increases, which can trigger an uncontrolled greenhouse effect fraught with extreme temperature fluctuations. The search for extraterrestrial life on exoplanets is associated with a number of serious challenges. First of all, it is difficult for scientists to determine the exact environmental parameters necessary to support life, especially when it comes to life forms other than those that exist on Earth. Modern science assumes that life on our planet is based on carbon and water, but theoretically, the existence of alternative life forms using other chemical elements, such as silicon, is permissible. This fact implies that it is impossible to exclude the possibility of the existence of organisms whose biochemistry is fundamentally different from everything known to mankind. In addition, a significant number of exoplanets that could potentially be habitable are separated from Earth by colossal distances. Unfortunately, at the current stage of technological development, humanity does not have the means to conduct a comprehensive study of these planets, including sending automatic research probes. At this stage, scientific research is limited to the analysis of data obtained using telescopes and other remote sensing methods. Even if a celestial body has favorable parameters for the origin of life, it may face powerful radiation or other harmful factors that make it unsuitable for the existence of biological forms. For example, powerful flares on the parent star or the absence of a dense atmosphere can negate all the prerequisites for the emergence of life. Despite this, the relentless search for potentially habitable exoplanets continues, and each year astronomers discover new celestial bodies of great interest for future research and possible colonization. One of the most exciting questions in exoplanet research is the possibility of life existing on these distant worlds and the forms it might take. Our understanding of life is traditionally based on carbon, water, and oxygen, but as science and technology advance, scientists are realizing that life can take on the most unexpected forms, different from those on Earth. This raises a legitimate question. Can life exist on exoplanets that is fundamentally different from that on Earth? And what conditions are necessary for this? Conventional ideas about life are often limited to a narrow set of conditions shaped by earthly experience. It is believed that living organisms require liquid water, a stable temperature regime, and an atmosphere with a specific chemical composition. However, this may be just prejudice based on the study of life on Earth. It is quite possible that there are forms of life that do not need the same elements or chemical processes as terrestrial organisms. Earthly life is based on carbon molecules, but scientists admit the possibility of life based on other chemical elements. One of the most likely candidates is silicon. Like carbon, this element is capable of forming long molecular chains that could potentially serve as the basis for biological structures. However, unlike carbon, silicon exhibits greater reactivity and is less stable in aqueous solutions, which may create obstacles to its use as a basis for life in the forms we are familiar with. In addition, scientists are considering the possibility of life forms using ammonia instead of water as a solvent. Ammonia is capable of supporting chemical reactions similar to aqueous ones, but at significantly lower temperatures. This opens up new perspectives for the search for life in cold worlds where water is frozen and ammonia remains liquid. In the distant reaches of space, on exotic planets like Titan, Saturn's mysterious moon, unique ecosystems may exist that are fundamentally different from those on Earth. Titan, shrouded in a dense atmosphere composed mainly of nitrogen and methane, is a world where methane, familiar to us as a product of organic decomposition, may play a key role in sustaining life. In this icy kingdom, life could have evolved using methane as a universal solvent, like water on Earth, and supporting complex chemical reactions at incredibly low temperatures. This opens up an exciting prospect. Life on exoplanets can take completely different forms than those we observe in our home world. We cannot dismiss the possibility of exotic life forms based on chemical processes radically different from those we are used to. One of the most exciting questions in the search for extraterrestrial life is the possibility of its existence in extreme conditions that would be considered uninhabitable on Earth. However, our own planet demonstrates amazing examples of life thriving in the harshest conditions. This includes ecosystems inhabiting deep-sea thermal vents where temperatures reach hundreds of degrees Celsius, as well as microorganisms inhabiting areas with elevated radiation levels or conditions of acute oxygen deficiency. These examples prove that life is able to adapt to the most incredible conditions, expanding our understanding of its potential forms and habitats in the universe. Extremophiles, these amazing creatures capable of surviving in the most inhospitable corners of our planet, provide science with a valuable key to unlocking the mystery of extraterrestrial life. Their remarkable adaptability opens up prospects for discovering living organisms, even where it would seem impossible. In particular, the subglacial oceans hidden on the moons of giant planets such as Europa at Jupiter and Enceladus at Saturn may be a cradle for life. Despite the freezing cold on the surface of these celestial bodies deep beneath the ice, there may be conditions favorable for the existence of organisms resembling terrestrial extremophiles. Probably the powerful ice shell serves as a reliable protection against harmful cosmic radiation and other external threats. Moreover, volcanic activity, so common on many exoplanets, is able to create local zones with elevated temperatures where water remains in a liquid state, even in conditions of general frost. Thus, active geological processes and volcanism can play a crucial role in sustaining life on planets that, at first glance, appear lifeless and uninhabitable. Currently, scientists are proposing numerous hypotheses about how life could have originated and evolved on other planets, under conditions different from those on Earth. It is quite possible that in other worlds, life arose and thrives in completely different conditions than we are accustomed to, challenging our understanding of the limits of what is possible. There is a belief in the scientific community that life beyond Earth may thrive in the most unexpected places, like ocean moons in our own solar system, such as Europa and Enceladus. Distant exoplanets sheltered by thick icy shells may hide subsurface oceans. In these aquatic worlds, protected from harmful radiation and extreme temperature fluctuations, all the necessary components for the origin and sustenance of life may exist. Chemical elements and energy sources dissolved in the depths of these oceans could serve as the basis for unique biological processes, different from those we observe on Earth, but capable of supporting the existence of simple organisms. Life may also be hidden in the atmospheres of exoplanets like Venus, where gaseous environments prevail. Microorganisms inhabiting the upper layers of the atmosphere, where temperature and pressure create favorable conditions for chemical reactions, could use solar energy to sustain their life, independent of the planet's surface. Furthermore, on exoplanets subjected to intense radiation, life could adapt to extreme conditions. Like hyperthermophilic organisms on Earth, living near volcanic vents and geothermal zones, extraterrestrial life forms could thrive at high temperatures and radiation levels, using chemical reactions occurring in these extreme conditions to obtain energy and survive. The question of the existence of life beyond Earth on distant exoplanets remains a matter of speculation and scientific hypotheses. Nevertheless, there are a number of factors that can influence the potential habitability of these celestial bodies. First of all, the chemical composition of the exoplanet plays a key role. The presence of life-giving moisture, a stable temperature regime, and an atmosphere capable of protecting against harmful cosmic radiation are the necessary conditions that create a favorable environment for the origin and development of life. It is planets with such characteristics that are of greatest interest for astrobiological research. No less important is the activity of the star around which the exoplanet orbits, because the star is the main source of energy for the planet. Stars with stability and constant radiation create the most favorable conditions for the development of life on planets in their gravitational field. However, exoplanets located too close to a star may be subjected to intense ultraviolet radiation, making it impossible for any form of life to exist on their surface. Conversely, exoplanets located too far from the star risk facing the problem of water freezing and extremely low temperatures, which also prevents the emergence of life as we understand it. However, we should not limit ourselves to terrestrial ideas about life. It is quite possible that life on exoplanets may exist in completely different, unexpected forms. It could be life based on the same chemical elements as on Earth, or it could be something fundamentally new, using, for example, ammonia or silicon instead of carbon. Deep scientific research and advanced technologies, which make it possible to accurately study exoplanets and analyze the composition of their atmospheres, open up exciting prospects in the study of the phenomenon of life beyond Earth. They allow us to expand the boundaries of understanding about potential forms of existence in conditions that now seem completely unimaginable. Discussions about the prospects for colonizing exoplanets raise complex technical and biological questions that require innovative solutions. Despite significant progress in the space industry, humanity does not yet have the full set of tools and knowledge necessary to overcome the challenges associated with long interstellar journeys and creating a stable, habitable environment on other planets. The primary task is to provide reliable housing for future colonists. Presumably, exoplanets that are potentially habitable will be characterized by extreme conditions, such as intense cosmic radiation, extremely low temperatures, or an unstable atmospheric composition. Therefore, there's a need to develop and create sealed biospheres that can effectively protect people from adverse external factors. One of the key aspects of successfully colonizing an exoplanet is creating an artificial atmosphere with an optimal composition and maintaining stable pressure. This means precisely controlling oxygen and carbon dioxide levels, as well as protecting against harmful impurities in the air. Life support systems must be exceptionally reliable, ensuring normal breathing and maintaining the health of the colonists for an extended period, possibly even decades. Providing colonists on exoplanets with everything they need to survive is no easy task. For a colony to not only survive, but thrive, a stable supply of water, food, and energy is required. A key element for long-term habitation on another planet is establishing a safe and sustainable ecosystem capable of providing the settlers with food and water. The issue of energy independence is equally important. Exoplanets located vast distances from their host stars receive minimal sunlight. In such conditions, alternative energy sources such as nuclear power or geothermal energy, provided there is volcanic activity on the planet, must be explored. Furthermore, advanced energy storage and distribution technologies must be developed to provide the colonists with everything they need during long journeys and life on the exoplanet. In the context of discussing the colonization of distant exoplanets, the problem that calls into question the very possibility of rapid communication between settlers and Earth, communication delay, cannot be ignored. It's no secret that some of these planets are millions of light years away from our home planet. This means that any message sent from Earth will only reach the distant colony after decades or even centuries. Such a delay imposes strict limitations on the ability to effectively manage the colony from a single center. This, in turn, dictates the need to create fully autonomous life support systems capable of functioning and developing virtually without constant communication with Earth. In this regard, one of the most exciting and complex tasks is terraforming exoplanets, the process of transforming the atmosphere and climate of a celestial body to create conditions suitable for terrestrial life. The essence of terraforming is to create a stable atmosphere that maintains an acceptable temperature and the presence of liquid water. A classic example that has intrigued scientists and science fiction writers for years is the idea of terraforming Mars. Although the red planet's atmosphere is currently too thin and cold for life as we know it, there is a hypothesis that increasing the temperature and density of the atmosphere could lead to liquid water on the surface of Mars, making it potentially habitable. Planetary transformation, known as terraforming, involves a set of measures aimed at adapting the environment of celestial bodies to human needs. The initial steps under consideration include innovations such as creating greenhouse complexes, increasing the concentration of carbon dioxide in the atmosphere, and using water resources rationally to raise the planet's temperature. However, when it comes to exoplanets located at significant distances from us and in little-studied star systems, the challenges of terraforming are multiplied. In such cases, more complex and technologically advanced methods become necessary. For example, creating artificial magnetic fields to protect the atmosphere from cosmic radiation becomes critically important. Genetic engineering of microorganisms capable of actively participating in the formation of a life-friendly environment is another promising direction. Nevertheless, implementing terraforming projects involves enormous resource costs and the need to develop technologies that are currently beyond our capabilities. We need to find fundamentally new approaches to influencing planetary bodies to create climatic and atmospheric conditions suitable for long-term human habitation. For successful colonization of exoplanets, a number of complex tasks related to resource extraction and redistribution must be solved. The planet must have accessible mineral resources suitable for construction, as well as energy resources such as fuel for energy production. One of the key aspects is water extraction. On some exoplanets, water may be present as ice deposits or underground oceans, which will require the development of specialized technologies for its extraction and processing. For Mars, for example, scientists suggest the presence of water ice in the polar ice caps and beneath the planet's surface, opening up prospects for its extraction using advanced engineering solutions. In the context of exploring distant exoplanets, agriculture emerges as a task of paramount importance, requiring innovative solutions. To provide colonists with essential food, it will be necessary to create artificial, carefully balanced ecosystems. These systems must be capable not only of cultivating a variety of plants, but also of effectively recycling waste, turning it into useful resources. Closed-loop systems, such as space greenhouses, could become the cornerstone of agricultural production in exoplanetary conditions. The most important requirement for such systems is their autonomy and sustainability, which will ensure a stable supply of necessary resources to the colonists over a long period of time. However, along with food security, the problem of biological risks poses a serious threat to exoplanet colonizers. Any ecosystem based on terrestrial organisms potentially exposes colonists to danger due to the possibility of encountering unknown diseases, viruses, or pathogens that may be lurking in the depths of a new planet. In this regard, the development of reliable systems for protection against biological threats becomes a priority. Genetic modification of humans and microorganisms may be the key to solving this problem. With the help of genetic engineering, scientists will be able to create organisms resistant to local conditions and capable of protecting colonists from pathogenic factors of the exoplanet. This approach is also applicable to the creation of new organisms designed to maintain balance in the planet's closed ecosystem, ensuring the sustainable functioning of the life cycle. Exoplanet exploration poses not only engineering challenges to humanity, but also complex questions related to ecology and ethics. It is important to realize that any change in the ecosystem of another planet can have serious consequences for its possible local flora and fauna. Even if there are no signs of life on the discovered planet, human interference in its ecological balance can lead to unpredictable results. At the same time, the colonization of other worlds raises important ethical questions about the right to explore alien planets and use their natural resources. It is necessary to carefully weigh how justified the intervention in the ecosystems of other worlds is and what rights we should have as creators of new settlements. These moral and philosophical dilemmas require special attention. The search for exoplanets and the prospects for exploring other worlds open up exciting prospects for humanity. However, like any significant scientific and technological achievement, this process is associated with ethical problems that cannot be ignored. One of the main issues facing scientists and society is the impact we will have on exoplanets and their ecosystems. When studying these planets, it is important to remember that their ecosystems may be vulnerable to the effects of terrestrial biology. The experience of environmental problems on Earth associated with the introduction of alien species can help to understand how human intervention in the ecosystem of another world can lead to unforeseen consequences. In this situation, the central ethical question is to determine the limits of permissible impact on other planets. Is it permissible to invade the biological processes occurring on exoplanets? Or should humanity limit itself to the role of an outside observer without disturbing the course of natural evolution? Imagine a situation. Signs of life are found on a distant exoplanet, even in its most nascent form. A dilemma arises. Do we have the right to interfere in its development, direct it, or are we obliged to allow evolution to take its course? One possible way to solve this complex problem is to develop a system of international agreements governing human activity in relation to exoplanets. It may be necessary to create strict environmental standards that ensure a responsible approach to scientific missions and colonization, taking into account the long-term sustainability of ecosystems and the potential existence of life. Finding a new home for humanity is not just an engineering task, but also a deep philosophical question. The desire to explore other planets and expand the presence of human civilization in the universe is inextricably linked with reflections on the place of man in the cosmic scale, on his purpose. Throughout its history, humanity has constantly asked questions about its origin and future. Space has always been a symbol of unexplored horizons, and the desire to conquer it has become not only a scientific challenge, but also an embodiment of human thirst for knowledge and progress. However, it was only with the development of space technologies that humanity gained a real opportunity to realize the dream of going beyond Earth. From a philosophical point of view, humanity's desire to find a second home in the universe raises profound questions about the responsibility that lies with intelligent beings. Should we seek a new abode simply because Earth has become uninhabitable, or because we are aware of the finiteness of our stay on this planet and strive to expand our horizons? This question exposes the essence of human nature. What is more important to us? Simple survival or the relentless pursuit of progress and expansion? Colonizing other planets raises existential questions about human identity. What transformations will occur when humanity settles in different parts of the cosmos? How will this affect our perception of Earth, our common home, and our place in the universe? Will settling on planets lead to a loss of connection with Earth? Or, on the contrary, will the expansion of humanity's habitat strengthen our attachment to the cradle of civilization? With the development of space technologies and opportunities for colonization, the question of humanity's environmental responsibility in space becomes acute. We have a duty not only to protect Earth from environmental disasters, but also to prevent the degradation of ecosystems on other planets. Given the problems of pollution and climate change that we face on Earth, it is important that the colonization of other planets does not become a repetition of these mistakes. We face the task of developing methods of sustainable space exploration that will avoid the environmental problems committed on Earth and preserve the fragile balance of exoplanets. As a promising solution for the exploration of exoplanets, the creation of closed ecosystems is being considered, designed to recreate Earth's conditions and ensure the stable existence of life in new worlds. These autonomous systems will not only provide colonists with everything they need, but also minimize the impact on the fragile ecology of exoplanets, preventing the depletion of their natural resources. Equally important is the development and implementation of global environmental standards that will regulate activities for the exploration of outer space. These norms are designed to protect new planets from the fate of Earth, preventing environmental disasters that may result from uncontrolled colonization. Space agencies such as NASA and other similar organizations should take on the role of guarantors of long-term sustainability and environmental safety in the process of exploring exoplanets. The question of interaction with extraterrestrial life forms, if any are discovered, is of particular importance. If life is discovered on an exoplanet, humanity will have to decide how to build relationships with other beings. Will we strive to study and understand these life forms, or will we prefer to keep our distance to avoid potential harm to our ecosystems and not provoke unwanted consequences for alien nature? Philosophical discussions about the rights of extraterrestrial beings come to the fore. If we discover life beyond Earth, should we recognize its right to independent existence and respect, or will we consider alien organisms as objects for research and possible colonization? This question calls into question the moral and ethical principles that define our attitude to life in all its manifestations, whether terrestrial or extraterrestrial organisms. Humanity, standing on the threshold of colonization and the search for new worlds, faces an existential question. How will the success of interstellar expansion affect us? Settling on exoplanets will inevitably call into question our collective identity and self-awareness as a biological species. Will we be able to find ourselves as a space civilization? Or will Earth forever remain not only the cradle, but also the spiritual center of our existence? Will we share the burden and triumph of colonization with other intelligent beings in the universe, or will we face a clash of civilizations? These questions open new horizons for philosophy, ethics, and science, which are called upon to play a decisive role in determining the future of space colonization. One of the most exciting aspects of exoplanet research is the steady approach of scientists to the discovery of planets potentially suitable for life. The only question is when exactly this will happen. Today, there are already a number of promising candidates who appear to have favorable conditions. However, final confirmation of their habitability will require years of painstaking research and observation. One of the main difficulties faced by scientists is the enormous distances between Earth and